Okay, I think it's recording. I think I hope so. Okay. Well, okay. So the idea of this it's mainly to understand the fundamentals of operational amplifiers. I think this today will be focus on that part because, well, operational amplifiers is actually one of the building blocks of many of the instrumentations, equipments that we use. That normally is the first stage just after we have the detectors signal, and there's many applications, and you will relate many of well, some of these examples and how the operational amplifier are configured to make some of the instrumentation that maybe you already know and you have seen in the labs, for example, no? So, okay. Well, this is not new for you. We have well, we have a basic representation of a detector is normally represented or modeled as a capacitor. So one of the very important characteristics of any kind of detector are the capacitance that they have. So that will actually affect how we process the signal from the detectors and how we characterize and we analyze the information from any kind of detector. So, okay, then, well, first, what is an operational amplifier? Or normally we can find it as op-amp. Well, the op-amps or operational amplifiers are devices that are DC coupled with very high gain. These have two inputs, two differential inputs that normally are single-ended output. So there's two differential input and one output. One of the properties is that they are very versatile. They are easy to configure, well, relatively easily compared with, for example, transistors. And you can, there are many types of functionalities for op-amps. Well, you can design different kind of preamplifiers to suit specific detectors and processing requirements. Basically, you adapt the signal from one detector to your electronics to later digitize somehow. Well, some parameters that we have to consider from preamplification circuits is a signal to noise ratio, and that's we decide a very high signal with respect to a noise. Also the range of the input, so we can actually see the full signal, that we don't lose information from, let's say, from low signals to the highest. We want also take care of the response time according to our needs. Power consumption is very important also, the dynamic range. Pulse pileup, so that's also related to the time response. And a common mode. This is common mode is related to the noise rejection, and maybe we'll see some details about this later. Okay, so
Can I have a question?
yes, sure.
Can you go back to the previous slide? What is the difference between the range of input signal and the dynamic range?
Dynamic range and actually they are both related. Range.
Because that's what I thought. I always thought that the dynamic range refers to the range of the input signal. So how robust is it, for example? But
I think the same. I don't remember from where I copied this, but not sure. Range of the input signal and dynamic. Actually could be the same because the range is basically the lowest you can deal with up to the highest. So, and basically that's the dynamic range. Range. Well, no, well, the range of the input. So you should know in which range your detector, in our case, it's working. So what is the lowest signal you will get from the detector and what is the highest? And the dynamic range, I think, is referring to the capability of the op amp, probably. So well, basically you have to match these two. We can think about like this, but yes, you are right. So there's not much difference, but probably it's just different stages. So it's not clear. But this
Okay,
is absolutely the
thanks.
same. So it's not a big deal. See, this is. I don't know if you're okay with this answer or.
Yeah, it's okay.
No, okay. Okay, so well, I showed you this last time. So basically, operational amplifier from inside, there is a range of different blocks made out of transistors, which at the end is encapsulated in something like this. Well, this is the electrical symbol, and we can represent all these blocks that this configuration of different kind of amplifiers made out of transistors in one single module that we can deal more easily, and it's much more convenient to use. So at the end, we have one non-inverter input, an inverter input, some power supplies, inputs also, and one output. So we will see in next slide. And first, I want to talk a bit what is a transistor first. We are not going in too much into deep with this because it's not the goal, but it's good to know from where it's come from this operation amplifier and why is that important and useful, no? So basically, transistor, it's a well very important component, which is it's an active device. This active component that can amplify, producing a signal with more power in the output. Not for example like passive component as resistor, coils, or capacitors. They basically they just can amplify. They can amplify signals, but they cannot deliver more power in the output. So well, it's logic that well, it's logical that the the highest power in the output needs also a power source. No, you need a power source, external power source to amplify signals, but that is achieved with this component, this active component. So the transistors. So a transistor is the essential ingredient of electronic circuit, from simplest amplifier, oscillators, and more elaborate circuits. And basically, it's the smallest components from integrated circuits. No, every electronics we know now not is are made of transistors, different kind of them. Well, here I introduce another reference. This actually is a very nice book. If you want, I can give you in PDF. It's very nice for electronics, so it's very well summarized and explained. But actually too much summarized, but it's very well explained. So just I will give you this reference later. Okay, so there are several types of transistors, but the basic one is something like this. Is We have two main kinds of transistor, well, configuration, which is NPN or PNP. That basically we can see these two configuration as two diodes connected from the anode in the case of NPN configuration, or from the cathode from the PNP configuration. And this, it depends how we connect this to some input signal, to a power source. We will have an output. Well, we will have a certain kind of output, no? So if we configure correctly this device, we have at the end in the output of the collector, well, we have this base, well, the how is it? How to say? Okay, so we have three inputs, let's say, of the in the transistor. We have a base, a collector, and in an emitter. And depending of how we configure all these three inputs, we can have some gain of current in the base of the transistor. So we will see how some very basic configuration of the transistor to get a specific response. So okay, so what we can do with a transistor? The most basic use of this device is we can use it as a switch. So basically, we can, for example, use it to drive a higher current with a lower current as an input, for example, from a microcontroller. This is like a very common use of it. The microcontrollers normally give very low current with some logic signal the output, and normally it's not enough to drive a LED, or if we want to put a LED with more power consumption, we cannot connect directly here because we can, for example, burn the circuit or the microcontroller. So what we do is to put the output of the device to one transistor. What we have here is we put some resistance to the base. This is the base, yes. Base, collector, emitter. Okay, we have the base, and this will put the transistor in saturation mode, and this will let the current go through the collector to the emitter, and then we will have a better higher current to the LED, and this well, this is the configuration as a switch. This is the very basic use of it. We can use, for example, for pulse generation, and it's a combination of this switch configuration using a capacitor that will charge and then discharge in a second stage of the circuit. And this will generate at the end some pulse that will be that the width of this pulse will depends on the capacitor and resistance values, no? So this is another, and also we can design a very basic amplifier. So here we have some feedback resistors that will allow the the circuit to generate a higher signal at the output. And well, the idea here, we will not analyze how this work exactly, but the idea here is that you see different blocks that are used to that use transistors to build some different type of responses. So we have something like emitter follower, which basically gives gives the same current from the input to the output. The same voltage from the input to the output, but higher current, for example, some switch, source current, another type of amplifier, common emitter, and common base amplifier. So different configuration for an amplifier and in uses of the transistor. So they're like small building blocks to create some amplifier. And then, there is also very important to understand operational amplifiers that there is a differential amplifier, which basically it's made of, you have two inputs where you can put same signal or different signal, depends on what you want to do. And at the end you have a single output. And here, this is related to the building blocks of the operational amplifier that we saw at the beginning. So what is here? The differential amplifier is a very common configuration to amplify different voltage between two input signals. In the ideal case, the output is entirely independent of individual signal levels. No? So only the difference of the two signals here matters, and we have some output depending of the inputs. And differential amplifier is the first stage, let's say, of the operational amplifier. And we have here, I think, yes. Yeah, and as explanation, what is here? So we have a differential amplifier at the input. We have a voltage amplifier close to the output. Then output amplifier. This is to provide current gain in the output. So, and then also some we have a current mirror blocks here made out of transistors. So this is a very complex thing. And yeah, that's it from here. So this is the general architecture of operational amplifier. So then, operational amplifier basically summarize all those blocks that we saw previously in this small block. So where we have the inverting input and non-inverted input, we have a single output. We have two voltage source, one positive and negative normally. In some cases, we have, depends for specific applications. There are some cases that we have only one source, one is to ground and one is to positive or negative, depending in specific application. But in general, this is the more general configuration for an op-amp. And when you see a bigger schematic circuit, you will find only this small this symbol for that. Probably you will see often if you are in instrumentation field. No, you will see something like this. Okay. Okay, now very general characteristics of operational amplifier. So key characteristics that we should know when we analyze what different type of configuration of an op-amp. So, these are technical characteristics. We have two differential inputs, which is the non-inverter and inverted input. We should take care of this, that not confuse this non-inverter in inverter as a negative or positive input. It's not the same. So it's just inverted and not inverted. This device, as it is, have a very high gain in the order of 10 to the 6 or even more. The input impedance for an ideal operational amplifier is infinite, so is very, very high. And low, and it has a very low impedance in the output. So these characteristics are keys to understand how this works. And regarding amplifiers configuration in radiation detector system, there are three different kinds, like more basic kind, which is voltage sensitive, current sensitive, and charge sensitive. Okay, then regarding the design of circuit using op amps, we have some kind of rules. I will put here quote marks because it's rules. Yes. Okay, there's some rules. Okay, so also here is important to remark key characteristic of op amps. So the op amps has a very high gain that is so high that a fraction of a millivolt between the input terminals. That is also important to remember that the the voltage we need is the difference of voltages between the inverted and not inverted terminal. So the fraction of a millivolt between the input terminals will swing the output over its full range. What does it mean? So here between these two terminals, we will have a difference of voltage. At the end, that's what it matters for the operational amplifier to amplify. And the full range of an op amp, it's basically the voltage that we have in the power source supplies from the positive and the negative. So the maximum voltage we can have is the voltage from the positive power supply, and the minimum will be the voltage that we have in the negative power supply. So, and here, if we don't configure with feedback loops, we will have very high gain. And the minimal change on the difference of these inputs will create some very high amplification that very easily can reach the maximum. So this is voltage Vs from the positive supply or the minimum. So it kind of saturate very easily with the very small change from the voltage difference on the inputs. Okay, so the first rule is that the output will try to do whatever is necessary to make the voltage difference between the inputs zero. So this will try to make somehow this difference between the inputs zero. So something will happen here in the output to try to make this different potential zero. Okay, so for example, the op amp will dry very little current from the inputs, and that is also very important to remember. That can go from 50 picoampere for some cases, and up to less than a picoampere for some other types of op amps. And the second rule is that the inputs draw no current. Basically, well, in the ideal case is we for the analysis we consider that the inputs draw no current between the two inputs. Okay, so okay. Okay, so we have these two rules, no? That the voltage difference want to be zero, and we don't draw any current from the inputs between the terminals. So the very basic application, like that can help us to understand this concept, is the non-inverting and inverting comparator, which is very basic configuration for an operational amplifier. So we have two inputs. This is not non-inverted and inverted. And depending on the difference between the inputs, we will have at the output the saturation level from the power sources that we have. For example, if the voltage in the input, in this case, the voltage in the input is from this is okay. We will have some reference voltage in the not inverted, and we will have some input level in the non-inverted input. So, for example, when the voltage in the input is larger than a reference voltage in the inverted input, and we will have in the output the positive voltage of the power source, that is plus VCC. And in the other case, when the voltage in the input is lower than in the reference, which is this one, the output will be minus VCC. No, is the negative power source. That is the saturation level from positive and negative power source. So and for this we have two modes: the non-inverted and inverted comparator. So this is the electrical circuit for this. We have, in this case, for the non-inverted, we use as an input the not inverted input, and we put some reference voltage in the inverted input. So in this case, we have well, actually, this level can be anything. For example, here we can put some specific voltage, or what is that? This variable resistor that we can configure manually, for example, and set some reference voltage, and then depending on and how the voltage in the input varies, we will have some output levels. For in this case, in a specific case, the power source in the negative power input, we have ground, so let's say 0. Yes, we have 0, and in the positive we have some positive voltage level. And the reference here will be basically the half of the power source voltage. So, but here we can configure as we want. And every time that the voltage in the input is lower than this half of the power source voltage, it'll be 0. And when every time it crosses over this reference voltage, VC/2, we will have the saturation level, which is the VCC, well, this voltage here. So this is a comparator. So, and for inverting comparator is very similar, but the reference voltage is going to the not inverted input, and the signal input is in the inverted input, and the voltage output looks like this. When it's lower than the reference voltage, we have the maximum voltage, VCC, and when it's over, we have 0 voltage, which is this ground, basically. So you see here already how op-amps are used for basic instrumentation things in high energy physics. which basically is a discriminator. It's also used for single or multi-channel analyzers. We will see this later, how it is also for fast ADCs, etc. So, okay, this is already, well, this is basic, but this is already something that we can see in real life for uh, everyday use equipment in physics. Okay, so also we can combine these comparators to create some a bit more elaborated circuits. So, for example, we have this window comparator, which basically we can create. We have two reference levels that we can choose to select one specific range of amplitude or voltage input. Here we have what we have here. So we have this is inverted comparator in the top, and this one is not inverter comparator. Here we can set specific ranges for reference, the upper range of this window that we want to select, and also the lower value of the window that we want to select, which is this one. So, and we create this selection window with two comparators. And this, for example, this one is basically a single or multi-channel analyzer. So an range of this is a window selection for that can be used for a single channel analyzer, for example. And also we can have a range of comparators with different levels of voltage input reference level. So in the input we have well, all the inputs are connected to the same one. Well, to the same input. This one is not inverted, and different voltage levels. And depending on the level in the input, we will have we will mm, we will activate one of the inputs depending on the variation of the input level here. So, for example, here when the voltage is lower, we will see this LED 4 activated. When it's higher, we will see the 3, the 2, the 1, and so on. Yep. So, okay, well, and this one is used for example, for fast ADC. This is the way the technique used to build the very fast analog to digital converters. Okay, up to here, some questions? No? Okay. Okay, so, well, here is the first a bit more complicated analysis of operational amplifier. So before we was seeing configuration of an op-amp which was not using any feedback from the output to the input. So we were just working with saturation or not saturation, depending if the input level was crossing or not some reference voltage in the other input. So in this case, we have some feedback resistor that will go to one of the inputs. So in the case of the inverter mode, is this feedback resistor is connected to the negative or to the inverted input. To this analysis, we have well, to know how this inverted amplifier works. And we have to remember some of the characteristics of the op-amp. So we have the inverted input and not inverted with a internal resistance. This is an equivalent operational amplifier scheme. So the impedance in the input we consider ideally as infinite and very large. The impedance and the output very low. And also we have to remember that the output will try to make the voltage difference between the two inputs zero, and the inputs is drawing no current between these two inputs. Okay, so so we have one input resistor when the voltage input is coming in. We have the feedback resistor, which is called R2, or more commonly is called RF, or feedback resistor. We have here two nodes. The node A, which is is connected to the inverted input, and the B, which is connected to ground. And this feedback, if we consider this feedback, we will see that well, we can rearrange a little bit just to understand what is happening here with the voltage and current. That since we have given that there will be no current drawn between the two inputs, and the difference on the inputs wants to be zero, we can consider here that the current from this node, from the node A to the ground is zero. So here, this thing actually is called a virtual ground. I have to write here. Just give me a second. This is virtual ground. Okay, so we have here something called a virtual ground, which is not a direct connection to the ground, but since the current drawn in between these two inputs is zero, but well, we can consider more or less as a ground. And the current flowing between the two well, we have to calculate this current that is flowing through the two resistors, R1 in the input and RF, which is the feedback. So here, to analyze this, we can see that the voltage in the feedback resistor it will be the same as the voltage in the output, and the voltage in the resistor 1 will be the same as the voltage in the input here. So, and if we calculate the currents here, we can see that the difference on the voltage input and output divided by the total resistance of this circuit will give us the current. And here, but since well, let me see. Okay, but also we can see that the current flowing in each resistor, well, has to be the same. Can be also calculated using the difference of the voltage in the input with the voltage in this node. Well, we use this current mesh. I don't remember how it's called in English, but this current is flowing from here to here. So we have that the voltage in the input minus the voltage in the node 8 is 0 divided by R. That should be also the current, and similarly for this part of the circuit. So, and since the voltage, why I wrote this, it should be A. So since the voltage A is zero, this voltage here is zero, we can simplify this equation, and we have this relation. So the voltage in the input divided by the resistor 1 is equal to the negative voltage in the output divided by the reference resistor. No, not the resistor, feedback resistor. And from here, well, this is very simple equation. We can see that we define that the gain will be basically the resistor, the feedback resistor divided by the resistor 1 in the input. And this will be equal to the volt minus the voltage output, so over the voltage in the input. And at the end, we have that the voltage output is equal to the gain negative times the voltage in the input. So this is how it is. We can configure, well, this is how we derive the equation to configure the operational amplifier to be a inverted amplifier. So and that's very simple. So any questions here? No? Okay. So, okay. So, well, as a homework, you will, for next lecture, please make the same thing, but for the not inverter amplitude amplifier. So that's homework for next time. And well, this is for you to more or less practice how this work. So I think this is important to understand how this work. So okay, no questions? You sure? So 1 second. Okay, so okay, so what we see before is basically voltage sensitive amplifier. And here, let me see. Okay, so well, here we have to take into account to go to something that is closer to the real world. We have to, well, we consider also that the ideal op-amp is considered to have infinite resistance here, but in reality, there's not a finite resistance, but also have some capacitance between the two inputs. And that is very close related to the for the design of a proper amplifier for a detector. Why? Because we have the model of a detector is a capacitor, and we have a capacitor, capacitance also in the input. So we have to take into account this, no, for the design and understanding of the behavior of the operational amplifiers. So okay, so then the voltage in the input will depend on the detector amplifier. The detector capacitance could be function of operation point. For example, well, yes, the detector works at an operational point, for example, at a certain high voltage or something. And also depends on the dimensions. So, well, as you know, capacitance of something the depends on the geometry of the device, the distance or the build of this, also the voltage of the power source of the detector. So there's many parameters that one has to consider to know the specific capacitance of a detector. So this is, well, needs to be calibrated and understood for each detector, even for the very similar detectors. The capacitance of each, let's say, modules, for example, I don't know, PMTs or RPCs or anything can vary. It can vary, can be have some variations, and that will affect the performance of an amplification. So the voltage in the input, you will see that it's like this, which is basically the charge. This is the charge of the source divided by the charge of the detector plus the capacitance of the detector plus the capacitance input of the operational amplifier. So here is already we can see here that there is a relation from the voltage we have here with respect to the characteristic of the detector and also the op amp. Okay, so um, the design principle of a voltage sensitive preamplifier is connected to a source or detector output, which is this one here. The input impedance RA, this one here, of the preamplifier is kept very large, as we saw from the typical characteristic of an op-amp or ideal characteristics. So that draws the minimal current from the source. So we saw already that. Then the voltage here in the input of the operational amplifier, it will be the voltage from the source, which is the detector, times the resistance, the internal resistance of the input impedance of the operational amplifier divided by the sum of the resistance of the source of the detector plus the resistance in the internal resistance of the op amp. So if we consider the ideal case where the op amp is infinite, ideally, or much larger than the resistance from the source or the detector. So we say that the voltage in the input is the same as the voltage in the source. So that's why we want this very large resistant input here. So that we can consider that the voltage in the input is basically the voltage from the source. And in the output, we'll have some amplification factor multiplied by the voltage in the input, which is the voltage from the source. Okay, so a simplified but realistic voltage sensitive amplifier with feedback resistor. That's why basically see in the previous slides. These are, let me see, with feedback resistor F times this. Let me see, simplified but realistic voltage sensitive amplifier with feedback resistor RF times capacitance of the detector is the combined detector and stray capacitance RS is the combined impedance. What is this? I forgot. Wait, let me remind what is this. So the voltage, okay, so we have, well, here we consider that the voltage source in the input, well, actually the signal from the input from the voltage source, is close related to, well, it's equal to the charge that is in the charge from the detector. So this stage here is the detector model, which with his resistance and his capacitance. So the voltage in the input will be basically the charge which is in the detector divided by the capacitance of this detector. And well, yes, the where the voltage output will be the amplifier factor. Actually, this will be negative. And the charge from the delivered by the detector divided by the capacitance from the detector. So where Q is the charge collected by the readout electrode, any detector we have, and the CD is the combined detector and stray capacitance. Well, here is the yes, the basically the capacitance of the detector plus I don't know, cables or something, anything we have between the input of the amplifier and the output of the detector. So this is the full capacitance of all chain just before the input of the operation amplifier from the yes, of this circuit.
I have a question.
Yep.
You said you said it will be negative. It's because it's connected to the inverter input.
Yes. Actually, if we see well, this A will be equivalent to the basically this here. Well, this thing here. Well, actually, this minus G, let's say. This
Yeah,
A.
and it's because it's in the inverter mode.
Yeah, exactly.
Okay.
Okay, so okay, now the charge sensitive configuration, and this is a very nice thing. And that's basically this is why, well, there is a reason to have this charge sensitive configuration as a, that's why this charge sensitive configuration is very commonly used for detector, well, in detectors. So the charge amplification only depends on well and how is controlled, how well controlled is the component in the feedback, which in this case is the feedback capacitor. So if you just as we saw here, the characteristics of the output will highly depend on the capacitance from our detector. So to calibrate and have well controlled the output, we have to know very well the characteristics in terms of capacitance or impedance of our detector. So that's and that can vary from channel to channel to module depending what we have. But the beauty of charge sensitive configuration is that we can this capacitance from the detector is low. The dependence on the capacitance of the detector is